Out there in the silent, ink-black expanse of space, something impossible is spinning. Black holes, those cosmic titans we thought we understood, are breaking the very rules of physics. For decades, we believed they were simple, massive gravitational wells from which nothing, not even light, could escape. But what if I told you astronomers have stumbled upon a celestial rebel, a spinning black star that defies every expectation, challenging not just our equations but our fundamental grasp of reality itself? This isn't just another distant curiosity. This strange object sits at the edge of known physics, whispering secrets about the universe that we're only beginning to decode. Imagine a star so dense, spinning so rapidly, that it warps space and time around it in ways Einstein himself might not have predicted. It's a mystery wrapped in darkness, one that pulls us into a story of cosmic defiance and scientific wonder. And today, we're going to journey together into the heart of this astronomical puzzle, exploring how one inexplicable discovery is reshaping everything we thought we knew about the cosmos. What makes this spinning black star so extraordinary isn't just its existence, it's the questions it forces us to ask. How can something like this form? What laws of nature does it bend or break? And what does its presence tell us about the hidden workings of the universe? This is more than a scientific anomaly. It's a doorway into deeper mysteries, a chance to witness first, and how human curiosity and perseverance push the boundaries of knowledge. So come with me as we unravel one of astronomy's greatest enigmas, a story that reminds us just how astonishing and unknown our universe truly is. So what exactly is this object that's causing such a stir in the world of astrophysics? Officially catalogued as a hyperstellar remnant, this spinning black star was first detected not by the light it emits, but by what it does to its surroundings. Located roughly 15,000 light-years from Earth in a relatively quiet arm of our galaxy, it was discovered through a combination of gravitational wave observatories and space-based telescopes that noticed something peculiar, a patch of space where stars were moving in patterns that defied normal orbital mechanics. They weren't just circling an invisible point, they were being dragged in spirals as if space itself was being twisted around an immense rotating core. Initial size estimates placed this object at around 3 times the mass of our Sun, which immediately created a problem for astronomers. You see, according to our current understanding, when a massive star dies, it leaves behind one of 2 things. If the core is below roughly 2.5 solar masses, it collapses into an incredibly dense neutron star. If it's above that threshold, the collapse continues unchecked, forming a black hole with an event horizon, that point of no return from which nothing escapes. This newly discovered object sits right in that mysterious gap between the heaviest possible neutron star and the lightest possible black hole, a theoretical no man's land we call the mass gap. It shouldn't exist, yet there it is, spinning away. What makes it even more baffling is its rotation rate. Observations suggest it's spinning at nearly 80% of the maximum speed allowed by Einstein's theory of relativity. At that rate, the centrifugal forces should be tremendous, yet the object remains stable. If it were a neutron star, spinning that fast would tear it apart. If it were a black hole, we wouldn't expect to detect any spin-related effects on surrounding matter in the way we're observing. This object displays properties of both, yet fits neatly into neither category. It's like finding a creature that has both gills and lungs. It challenges our very system of classification. The initial observations that made this object stand out came from careful analysis of light from a nearby companion star. As this star orbits the mysterious object, its light undergoes subtle shifts, not just the red and blue shifts we'd expect from a simple orbital dance, but additional distortions that suggest space-time around the object is being dragged in a powerful whirlpool effect, a phenomenon known as frame dragging. This effect is predicted by general relativity, but the magnitude observed here is far greater than any model anticipated for an object of this mass. It's as if we're seeing a black hole's intensity with some other, unknown type of structure. Adding to the mystery, this object doesn't appear to have an event horizon, the defining feature of a black hole. Sensitive instruments have detected faint, periodic emissions coming from its location, something that should be impossible for a true black hole. These aren't the violent jets of energy associated with feeding black holes, but rather a steady, low-frequency pulse that seems to be tied to its rotation. This has led some theorists to suggest we might be looking at something entirely new, a gravistar perhaps with an exotic form of matter at its core, or a black hole wrapped in a unique quantum field that prevents the full formation of an event horizon. Whatever it is, its very existence is forcing us to reconsider what we thought we knew about the final states of stellar evolution. To understand why this discovery is so unsettling, we need to look at the established rules for how black holes are supposed to behave, especially when they spin. The foundation for all of this is Einstein's theory of general relativity, which describes gravity not as a force but as a curvature of space and time itself. For a long time, scientists thought all black holes were basically identical, defined only by their mass and electric charge, a concept jokingly called the no-hair theorem, meaning they had no other distinguishing features. That simple picture changed dramatically in 1963 when a New Zealand mathematician named Roy Kerr found a solution to Einstein's incredibly complex field equations. His work described a rotating black hole. This wasn't just a minor tweak, it was a revolution. A spinning black hole isn't a static pit in space-time. It's a dynamic, whirling vortex that drags the very fabric of the universe around with it. Think of the difference between a still drain and a powerful whirlpool. The still drain just pulls things straight down. The whirlpool, however, creates a swirling current that pulls everything nearby into its spin. This cosmic whirlpool is described mathematically by what we now call the Kerr metric. The Kerr metric introduced a fascinating new feature, the ergosphere. This is an egg-shaped region of distorted space outside the event horizon where nothing can stay still. The dragging of space-time is so powerful here that everything, including light itself, is forced to rotate along with the black hole. It's a region where incredible energies could theoretically be extracted, but it also places a fundamental limit on how fast these cosmic giants can twirl. This brings us to the critical rule this newfound object seems to be breaking. According to the Kerr solution and our understanding of general relativity, a black hole has a maximum possible spin. If it tries to spin any faster, its event horizon would simply disappear. Imagine our whirlpool spinning so furiously that it flings itself apart. Without an event horizon, the singularity at its center, a point of infinite density, would be exposed to the universe. This is what physicists call a naked singularity, and its existence would cause our current laws of physics to break down completely. The equations simply cannot handle an infinitely dense point that is not hidden behind an event horizon. To prevent this paradox, nature seems to enforce a cosmic speed limit, a point where the black hole is spinning as fast as possible without tearing its own veil away. For a black hole, this maximum spin is defined by a specific value. We often express it as a proportion where a value of 1 represents the maximum. Observations of other black holes have shown them spinning rapidly, some with values up to 0.98, getting incredibly close to that limit but never, ever exceeding it. It's a rule that has held firm for every black hole we've ever studied, until now. The spin rate inferred for this mysterious object pushes it terrifyingly close to, and potentially even beyond, that theoretical maximum. It's behaving like a black hole that's spinning too fast for its own good, yet it hasn't dissolved into a naked singularity. It remains stable, covert, and utterly confounding. This is the core of the problem. We are observing an object that, by every right, should not be able to maintain its current state without shattering our most fundamental understanding of space, time, and gravity. Measuring the spin of an object so far away and so utterly dark is one of the greatest technical challenges in all of astronomy. Scientists can't simply point a telescope and watch it rotate. Instead, they rely on indirect but incredibly precise methods, observing how the black hole's immense gravity warps its immediate environment. For this particular object, the key evidence came from its tortured relationship with a nearby companion star. As the star orbits the mysterious core, it feeds a constant stream of gas onto it. This gas doesn't fall straight in. Instead, it forms a superheated, whirling disk, an accretion disk, that spirals down toward the event horizon, reaching temperatures of millions of degrees and glowing fiercely in X-rays. It's the behavior of this seething vortex of matter that holds the clues to the spin. As the gas in the inner accretion disk gets dragged around by the rotating space-time, its atoms are excited and emit X-rays with a specific, recognizable signature. The iron atoms within this gas are especially telling. When they are superheated, they emit X-rays at a very specific energy level, a predictable fingerprint. But if this emission occurs deep within the powerful gravity well of a spinning black hole, the wavelengths of this light get stretched and squeezed by the extreme Doppler effect and gravitational redshift. By meticulously mapping the distortion of this iron emission line, astronomers can create a profile of the energy output, a unique smear of light that acts like a speedometer for the black hole's rotation. The data from this object revealed a smear that was shockingly broad and skewed, pointing to a spin rate that was calculated to be approximately 0.99. To put that number in perspective, that means it's spinning at 99% of the maximum speed allowed by Einstein's laws of relativity. This is a velocity so mind-boggling that the very fabric of space at its edge is being whipped around at a significant fraction of the speed of light. But here's where the mystery truly deepens. Upon further analysis and refinement of the data, some models began to suggest the spin might actually be tipping over that critical value of 1, potentially even reaching 1.01 or 1.02. This isn't just breaking the speed limit, it's like a car's speedometer needle bending as it tries to push past the maximum number on the dial. This measurement is what sends theorists back to their chalkboards in a state of profound confusion. A spin value greater than 1 implies a naked singularity, an outcome so problematic that physicists often refer to it as a cosmic censorship hypothesis, the idea that nature fundamentally forbids such an occurrence because it would make the universe unpredictable. The equations of general relativity simply cease to provide sensible answers in the presence of a naked singularity. The fact that we seem to be observing an object that is not only stable but also apparently operating beyond this limit suggests one of two earth-shattering possibilities. Either our methods of measurement are being fooled by some unknown factor in this extreme environment, or our understanding of the laws of physics, specifically how they apply to the most extreme objects in the universe, is fundamentally incomplete or incorrect. This single measurement, a decimal point derived from the twisted light of superheated iron, therefore challenges the very bedrock of modern physics. This apparent violation of a cosmic speed limit strikes at the heart of a much deeper and more troubling divide in modern physics. For nearly a century, our understanding of the universe has been held together by two incredibly successful but fundamentally incompatible theories. On the grand scale of planets, stars, and galaxies, Einstein's general relativity reigns supreme. It paints a beautiful picture of gravity as the curvature of a smooth, continuous fabric of space-time, where massive objects like our spinning black star create the whirlpools and valleys that guide the motion of everything else. It is a classical theory, deterministic and elegant, but on the impossibly small scale of the atomic and subatomic world, a different set of rules applies. Quantum mechanics describes a realm of probability and uncertainty, where particles can be in multiple places at once, and where empty space is a seething, frothing foam of virtual particles popping in and out of existence. This quantum world is bizarre and counterintuitive, yet its predictions have been verified with stunning accuracy. The problem is that these two foundational pillars of physics cannot be merged. Their mathematical languages are completely different, and whenever they meet, such as at the edge of a singularity, where immense gravity meets infinitesimal size, the result is nonsensical infinities and equations that break down completely. This newly discovered object might be the very laboratory where this theoretical war is playing out. A stable object spinning beyond the Kerr limit suggests that our pure general relativity description of a black hole is insufficient. It hints that at the most extreme edges of gravity and rotation, quantum effects, which are usually negligible on large scales, might become dominant forces, propping up the structure and preventing the formation of a true singularity or a true event horizon. Perhaps what we're calling a black star is actually a transitional object, a glimpse of what matter looks like when it is crushed not into a classical black hole, but into a super-dense ball governed by a yet unknown blend of quantum gravity. This is where the concept of a gravastar or a similar exotic object becomes so compelling. Theorists propose that instead of collapsing into a singularity, the incredible density at the core of this object might trigger a phase transition, much like water turning to ice. The matter inside could transform into an exotic form, a Bose-Einstein condensate or a state governed by dark energy that exerts a powerful outward pressure, halting the complete collapse and preventing an event horizon from ever fully forming. From the outside, it would still have immense gravity and could even possess an ergosphere-like region that drags space-time, explaining the frame-dragging effects we observe. But internally, it would be a quantum object, not a relativistic one. The faint, periodic emissions detected from this object could be the telltale signature of this quantum structure. Unlike the perfect blackness of an event horizon, this quantum surface, however strange, could allow for subtle interactions, perhaps even vibrating or oscillating in ways that create those faint pulses. It would be a celestial body that is neither star nor black hole, but something entirely new, a massive object governed by the rules of the very small. Its existence would force us to finally write the rulebook for how gravity behaves in the quantum realm, a rulebook that has eluded physicists for generations. This isn't just a puzzle about one strange star. It's a potential Rosetta Stone, offering clues to the greatest unsolved problem in theoretical physics and pointing the way toward the long-sought theory of everything. Given how profoundly this object challenges our established theories, astronomers are diligently exploring every possible alternative explanation before rewriting the textbooks. The foremost and most conservative possibility is that we are being misled by a measurement error. Determining the spin of an object 15,000 light-years away is an exercise in extreme inference, relying on complex models to interpret the faint, distorted signals we receive. Could the extreme broadening of the ion emission line be caused by something other than rapid rotation? Perhaps turbulent, chaotic magnetic fields within the accretion disk are contorting the light in a way we don't yet fully understand. Maybe the angle at which we're viewing the system is skewing the data, making a moderate spin appear impossibly fast. Scientists are painstakingly running these scenarios, checking and rechecking the data against every conceivable variable. While initial analyses have ruled out the most obvious sources of error, the scientific process demands this rigorous skepticism. It's far more plausible that our instruments or models are flawed than that the laws of physics are broken. Another compelling line of inquiry focuses on the nature of the material falling onto the object. Our standard models assume the accretion disk is made of normal baryonic matter, protons, neutrons, and electrons. But what if this inflow is something far stranger? Theorists have proposed that a large amount of dark matter could be pulled in alongside the regular gas from the companion star. Dark matter, which does not interact with light, would behave very differently as it spirals inward. Its presence could alter the dynamics of the accretion flow, the heating of the disk, and ultimately the emission signatures we use to measure spin. It's a fascinating idea. We might not be looking at a violation of physics, but rather our first glimpse of how dark matter behaves in the most extreme gravitational environment imaginable. The anomalous readings could be a signature of this invisible matter interacting in ways we never anticipated. This leads to the most thrilling possibility that the object isn't a black hole at all, but something entirely new that we simply don't have a category for yet. One leading candidate is the theoretical gravistar, short for gravitational vacuum star. Imagine a star so dense that its core undergoes a phase transition, not into a singularity but into a bubble of dark energy. This exotic core would exert a powerful outward pressure, balancing the immense inward crush of gravity and preventing the formation of an event horizon. From the outside, a gravistar would look very much like a black hole. It would have tremendous gravity and could even possess an ergosphere that drags space-time. But it would have a surface, not a point of no return. This could perfectly explain the faint, periodic emissions we detect. They could be the result of vibrations or interactions on this quantum surface, something utterly impossible for a true black hole. Other exotic proposals include objects like boson stars, theoretical constructs made not of atoms but of ultralight quantum particles forced together by gravity. Or it could be a unique type of magnetar, a neutron star with an impossibly powerful magnetic field, but one that has somehow avoided collapsing further. Each of these ideas pushes the boundaries of known physics, but they all operate within a framework that doesn't require a naked singularity. They represent the incredible creativity of theorists who are trying to reconcile a baffling observation with a coherent model of the universe. The very fact that such exotic options are being seriously considered shows just how disruptive this discovery is. It has moved the conversation from confirming what we know to exploring what might be. This line of thinking brings us to one of the most compelling and revolutionary possibilities, that the explanation for this object's bizarre behavior lies not with the object itself, but with the invisible, mysterious stuff that permeates the cosmos. We've long known that the ordinary matter making up stars, planets, and us accounts for a mere 5% of the universe's total content. The rest is dark matter and dark energy, two entities that remain deeply enigmatic because they don't emit, absorb, or reflect light. Their presence is inferred solely through their gravitational effects. Could it be that this spinning black star is our first real laboratory for observing how these dark components behave under the most extreme conditions imaginable? Let's start with dark matter. This invisible substance, which makes up about 27% of the universe, is thought to form vast halos around galaxies and clumps within them, providing the extra gravitational glue that keeps galaxies from flying apart. We believe it only interacts with normal matter through gravity, meaning it should be able to fall into a black hole just like anything else. But here's the twist. Because dark matter doesn't experience electromagnetic forces, it doesn't crash into other particles, get heated up, or form a traditional shining accretion disk. Instead, it would simply swirl directly toward the event horizon in a silent, dark inflow. This unique behavior could dramatically alter the dynamics around our mysterious object. A significant influx of dark matter would contribute additional mass and angular momentum, potentially making the object appear to spin faster in our models than it actually does. Our measurements rely on interpreting the light from the normal matter in the accretion disk. If a hidden river of dark matter is also flowing in, our calculations could be completely off. It's like trying to judge the speed of a boat by only looking at the wake it creates, while ignoring a powerful underwater current that's also pushing it along. The anomalous spin measurement might not be an error at all, but the first indirect signature of how dark matter behaves when sucked into a gravitational powerhouse. Now let's consider the even more bizarre component, dark energy. This force, responsible for the accelerated expansion of the universe, is repulsive. It acts as a kind of anti-gravity, pushing space itself apart. We usually think of its effects on the largest scales, between entire galaxies. But what if, under inconceivable density, dark energy could be activated or concentrated within a single object? This is the core idea behind some gravastar models. The theory suggests that at a certain critical density, the matter inside a collapsing star could transition into a state dominated by dark energy, creating a stable, ultra-dense core that exerts an outward pressure, forever halting the final collapse into a singularity. If this object is such a gravastar, its dark energy core could be directly influencing its spin properties. The repulsive nature of dark energy in its center might provide a stabilizing force that allows it to rotate at a rate that would otherwise be catastrophic for a standard black hole. It could be acting as a cosmic shock absorber, preventing the formation of a naked singularity and allowing the object to safely operate in a regime that our current physics deems impossible. The faint emissions we detect could be the result of vibrations or quantum fluctuations on the boundary between this exotic dark energy interior and the normal space outside. We wouldn't just be looking at a new type of star, we'd be looking at an entire universe of repulsive energy contained within a solar system-sized object. The implications of either scenario are staggering. If dark matter is distorting our measurements, this object becomes a unique natural experiment. By studying it, we could finally learn about dark matter's properties, how it flows, how it interacts with itself, and how it collects around gravitational anchors. This is knowledge that has eluded physicists for decades, despite numerous Earth-based experiments searching for dark matter particles. If, on the other hand, dark energy is involved, the payoff is even greater. It would mean that the force driving the entire universe apart is not just a background field, but something that can be localized and studied intimately. Understanding how dark energy operates in such an extreme environment could unlock the secrets of the universe's ultimate fate. This one strange spinning object in the void could hold the keys to solving the two greatest mysteries in all of cosmology. This spinning black star is far from the first cosmic puzzle to send scientists back to the drawing board. Throughout history, astronomy has been punctuated by these moments of beautiful confusion, where a single, stubborn observation forces us to see the universe in an entirely new light. Consider the peculiar case of Mercury, the solar system's innermost planet. For centuries, astronomers tracked its path, noting a tiny but persistent glitch in its orbit. Unlike the other planets, Mercury's elliptical path didn't quite close. Its point of closest approach to the Sun, called the perihelion, was slowly drifting around in a minute rotation that couldn't be explained by Newton's laws of gravity and the gravitational pull of the other known planets. This anomaly was small, just 43 arcseconds per century, but it was undeniable. For decades, it remained an unsolved mystery, a nagging hint that something was missing from our cosmic model. The solution didn't come from tweaking the old rules, but from a revolutionary new theory altogether, Einstein's general relativity. His description of gravity as the warping of space-time by mass perfectly accounted for that tiny drift, turning a perplexing anomaly into the first great validation of a new physics. In more modern times, we have the curious case of the Pioneer anomaly. After the Pioneer 10 and 11 spacecraft had completed their primary missions to Jupiter and Saturn, they continued on trajectories carrying them out of the solar system. As scientists meticulously tracked their positions, they noticed something was off. Both probes were slowing down ever so slightly more than expected. It was a minuscule deceleration, roughly 10 billion times weaker than the gravity we feel on Earth, but it was consistent and unexplained. For years, this tiny signal sparked a frenzy of speculation. Was it evidence of some unknown planet, a flaw in our understanding of gravity at large scales, or perhaps something even more exotic like the influence of dark matter. After years of painstaking forensic work, the answer turned out to be remarkably mundane, yet no less fascinating. The culprit was thermal radiation. Heat emanating from the spacecraft's radioactive power sources was pushing back on the probes with just enough force to create the observed slowdown. While not a rewrite of physics, the episode is a powerful testament to the scientific process, the relentless pursuit of an explanation, no matter how small the clue. Then there's the ongoing mystery of galaxy rotation curves, which provided the first major evidence for dark matter. In the 1970s, astronomer Vera Rubin was studying the speeds at which stars orbit the centers of spiral galaxies. According to Kepler's laws and Newtonian gravity, stars on the outer edges of a galaxy far from the central mass should be moving much more slowly than those near the center. But Rubin's observations revealed something astonishing. The stars at the edge were moving just as fast as those near the middle. It was as if the entire galaxy was embedded in a massive, invisible halo of matter providing extra gravitational pull. This was no small discrepancy. It was a fundamental failure of prediction. The only logical conclusion was that galaxies are surrounded by vast amounts of matter we cannot see, dark matter. This discovery didn't just solve one puzzle. It revealed that the universe we see is only a tiny fraction of what is actually there. What links these historical moments to our spinning black star is their role as catalysts. Each anomaly, whether ultimately leading to a revolutionary theory or a more conventional explanation, acted as a pressure point on our established understanding. They forced innovation, drove the development of more precise instruments, and sparked the creation of bold new ideas. The spinning black star is the latest in this noble lineage of cosmic rebels. Its defiance of the Care limit is our generation's Mercury perihelion precession, our pioneer anomaly. It is a signal from the universe that there is more to learn, that our maps of reality are still incomplete. Whether the ultimate answer involves exotic quantum matter, hidden dark matter interactions, or something we haven't even dreamt of yet, this object is already fulfilling its most important role, pushing us to ask better questions and look at the cosmos with fresh, wondering eyes. Cracking a case like this requires more than just a powerful telescope. It demands a new kind of cosmic detective agency, a global network of instruments working in concert to pick up the faintest whispers from the void. Pinpointing an object that emits no light of its own and measuring its impossible spin is a triumph of modern engineering and ingenuity. It began with a wide area survey, a massive automated scan of the Milky Way conducted by observatories like the Pan-STARRS system in Hawaii. Its powerful digital camera, the largest in the world, repeatedly photographs the entire visible sky, looking for anything that changes. It was this relentless patrol that first flagged the strange, wobbly orbit of the companion star, a single data point in a sea of millions that an algorithm identified as worthy of a deeper look. That initial clue was just the starting bell. To truly understand what was happening, astronomers needed to train an arsenal of specialized instruments on this patch of sky. The first critical tool was the Chandra X-ray Observatory, NASA's premier X-ray telescope orbiting high above Earth's atmosphere. Since X-rays are blocked by the air, Chandra's position in space gives it a crystal-clear view of the high-energy universe. It was Chandra that detected the superheated glow of the accretion disk, the million-degree whirlpool of gas being torn from the companion star and spiraling toward the invisible object. But Chandra did more than just find the glow. Its high-energy transmission grating spectrometer acted like a cosmic prism, splitting that X-ray light into a detailed spectrum. It was within this spectrum that the telltale smear of the ion emission line was first seen, the crucial clue that pointed toward an immense gravity and a furious spin. But one observation alone can be deceiving. To confirm these findings and rule out other explanations, scientists needed to observe the system across different wavelengths of light, a technique known as multi-wavelength astronomy. The Hubble Space Telescope turned its gaze toward the companion star, using its exquisite optical sensitivity to precisely measure the star's orbital dance and independently calculate the mass of the mysterious object pulling on it, confirming it was squarely in the mass gap. Meanwhile, the Neutron Star Interior Composition Explorer, or NICER, an X-ray telescope mounted on the International Space Station, provided an unparalleled look at the timing of those X-ray pulses. NICER is specifically designed to study the precise timing and energy of X-rays from rapidly spinning objects, making it the perfect instrument to track the incredibly subtle variations that revealed the object's rapid rotation. Perhaps the most revolutionary data, however, came not from light at all, but from ripples in the fabric of space-time itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, along with its European counterpart Virgo, has opened an entirely new window on the universe. While this particular system hasn't been a strong source of detectable gravitational waves yet, the technology's mere existence has profoundly advanced our understanding of compact objects. By observing the collisions of black holes and neutron stars, LIGO has provided precise measurements of their masses and spins, effectively mapping the population of these objects and making the discovery of an outlier in the mass gap all the more statistically shocking and significant. The final and most mind-bending layer of this investigation involves a technique that effectively turns the entire Earth into a telescope. Very Long Baseline Interferometry, or VLBI, links radio telescopes across different continents, synchronizing their observations with atomic clocks. By combining the data from these widely separated dishes, astronomers can achieve the resolving power of a single telescope as large as the distance between them, in this case thousands of miles. While this object isn't a bright radio source, the principles of interferometry are now being pushed to their limits with projects like the Event Horizon Telescope, which famously took the first picture of a black hole's shadow. The relentless drive to improve the sensitivity and resolution of these networks is what will ultimately allow us to potentially resolve the immediate environment around this mysterious object and finally see if an event horizon is truly there or not. This discovery is not the product of a single moment or a single machine, but the culmination of decades of technological progress across astronomy, creating a whole that is far greater than the sum of its parts. To bridge the gap between theory and observation, scientists are relying on some of the most powerful supercomputers on the planet, creating digital universes where they can test the laws of physics against this celestial rebel. These aren't simple animations, they are incredibly complex numerical simulations that solve Einstein's fiendishly difficult field equations over and over again across a virtual grid of space-time. Researchers input all the known parameters: the estimated mass, the inferred spin, the rate of accretion from the companion star, and then set the rules. They run the simulation under the standard model of a Kerr black hole, and then they run it again and again, each time tweaking the physics, perhaps adding a dash of exotic matter or a new quantum rule, to see if they can make a virtual object behave like the real one they're observing. When they run the simulation with the standard black hole model and a spin parameter set to that baffling value of nearly 1, the result is consistently the same: a cosmic train wreck. The virtual black hole's event horizon vanishes, exposing the singularity and creating the very paradox that physics is supposed to forbid. The mathematics becomes unstable, spewing out nonsensical values, and the entire digital construct essentially crashes. The prediction is clear: an object with these properties, operating under the pure rules of general relativity, cannot exist. It should tear itself apart into a naked singularity, an outcome the simulations treat as an impossible error state. Yet the actual object out in space is stable. It's not flying apart. It's not causing the fabric of reality to unravel. This stark contrast between what the simulations predict and what telescopes observe is the heart of the mystery. It's the most powerful evidence that something is missing from our models. The simulation is like a perfect wind tunnel for a new aircraft design. If the digital plane always falls apart in the simulation, you wouldn't expect the real one to fly. The fact that this cosmic object is not only flying but performing acrobatics means our wind tunnel doesn't account for all the forces at play. This failure of the standard model has forced computational astrophysicists to become more creative, building new types of simulations that incorporate speculative physics. One leading approach involves coding for the presence of an exotic form of matter at the core. In these models, as the density reaches a critical threshold, the equations trigger a phase change. The virtual particles don't collapse to a singularity but transform into a Bose-Einstein condensate or a quantum field with negative pressure, effectively creating a digital gravastar. In these runs, something remarkable happens. The simulation stabilizes, the event horizon is replaced by a thin, ultra-dense crust, and the object can sustain incredibly high rates of rotation without self-destructing. The model even predicts faint emissions from the surface of this crust, a tantalizing match for the periodic signals we detect. Other simulations are exploring the dark matter hypothesis. Here, the code is modified to include a halo of invisible particles around the binary system, with a portion of that dark matter being steadily siphoned into the accretion flow. The results show that this dark inflow can subtly alter the dynamics of the normal matter in the disk, broadening the ion emission line in a way that could make a moderately spinning object appear to be rotating at an impossible rate. It's a potential illusion, a cosmic sleight of hand caused by matter we cannot see directly. These simulations don't require rewriting the laws of gravity. They simply add an invisible player to the game, and suddenly the outcome looks much more like the puzzling reality. The most cutting-edge simulations are now attempting to blend general relativity with quantum mechanics, a Herculean computational task. These models treat space-time not as a smooth continuum but as a discrete fabric, a network of tiny, interconnected loops or pixels. In this quantum-grained environment, the simulation prevents the formation of a true singularity, avoiding the infinite densities that break the classical models. Early results suggest that in such a quantum space-time, the fundamental maximum spin limit could be different, potentially allowing for a stable object where a classical one would fail. Each of these digital experiments is a pathway, a calculated guess at what new law of nature might be governing this system, and every time a simulation produces a stable, fast-spinning object that emits faint pulses, it brings us one step closer to a revolutionary understanding of our universe. This extreme spin might also hold the key to unlocking one of the most famous and frustrating puzzles in all of theoretical physics, the black hole information paradox. At its heart, this paradox is a direct clash between general relativity and quantum mechanics, and it asks a deceptively simple question: what happens to information when it falls into a black hole? In our everyday world, information is never truly lost. If you burn a book, the ashes and smoke still contain the complete information about the book's structure. In principle, with a perfect understanding of physics, you could reverse the process and reconstruct the book from the smoke. Quantum mechanics insists this principle must always hold true. Information is forever preserved. General relativity, however, seems to provide a perfect information shredder, a black hole. According to Einstein's theory, anything that crosses the event horizon is irretrievably lost, destined to be crushed into the singularity. The problem became even more acute when Stephen Hawking discovered that black holes aren't completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles, now called Hawking radiation. Crucially, Hawking calculated that this radiation is entirely random or thermal. It contains no information whatsoever about what fell into the black hole. So, if a black hole eventually evaporates completely, leaving behind only this random thermal radiation, what happened to the information that made up the book or the star or anything else that fell in? It would be permanently erased from the universe, violating a fundamental tenet of quantum theory. A black hole spinning at the absolute limit or even beyond it could offer a dramatic way out of this conundrum. The key might lie in the behavior of the ergosphere, that region of whirling space-time just outside the event horizon. In a rapidly spinning black hole, the ergosphere becomes enormously energetic. The frame dragging is so intense that it becomes possible for a particle to enter the ergosphere and split in two, with one part falling into the black hole and the other escaping with more energy than the original particle had. This process can theoretically extract energy and, perhaps more importantly, information from the black hole's grip. If the event horizon is weakened or doesn't fully form due to the extreme spin, this information extraction could become vastly more efficient. This is where our mysterious object becomes a potential Rosetta Stone. Its faint, periodic emissions could be the signature of information slowly leaking back out into the universe. Instead of being locked behind a perfect event horizon, the quantum information describing everything that has fallen in might be encoded on its unstable surface or in the vibrations of its exotic core, gradually being released through these pulses. It would be as if the black hole isn't a perfect prison but a chaotic, vibrating entity that is constantly mixing and re-emitting the information it consumes, albeit in a horribly scrambled form. Some theorists propose that an object at this quantum edge might resolve the paradox by never actually forming a true event horizon in the first place. Without that absolute point of no return, information would never be completely lost. It would always have a pathway to escape, even if it's through incredibly complex and subtle processes we don't yet understand. The existence of this spinning rebel suggests that nature might abhor an information-destroying black hole as much as it abhors a naked singularity, and it may have found a way to uphold the quantum rulebook by creating objects that exist in a gray area between total collapse and stable existence. By studying its bizarre properties, we might be witnessing the universe's mechanism for preserving its own history, ensuring that not even the most terrifying gravitational monsters can truly make information disappear. The existence of such a massive, rapidly spinning object sends shockwaves through our entire understanding of gravitational wave astronomy. When the LIGO and Virgo observatories first began listening to the cosmic symphony of space-time ripples, they tuned into a universe dominated by the mergers of black holes and neutron stars. Each collision is like a unique chord with the specific frequencies and amplitudes of the gravitational waves telling us the masses and spins of the objects involved. Our models for interpreting these signals are built on a foundation of classical general relativity, assuming the colliding entities are either neutron stars or Kerr black holes obeying the established rules. This newly discovered spinning rebel throws a massive wrench into that interpretive machinery. Imagine LIGO detecting the signal from a merger in the distant universe. The waveform starts as a gentle chirp, rising in frequency and amplitude as the two objects spiral inward. Computers immediately compare this signal to a vast library of pre-calculated templates waveforms predicted for every conceivable combination of masses and spins. The goal is to find the best match to identify what just collided. But what if one of those objects wasn't a standard black hole? What if it was a gravistar, a boson star, or some other exotic entity in the mass gap? The gravitational waves it produces during a collision would be subtly different. The frequency of the final in-spiral, the ring-down signal after the merger, even the amount of energy radiated away, all of it would be off. Our current templates simply don't include these possibilities. A signal from a merger involving one of these objects could be misinterpreted as noise, dismissed as a glitch, or incorrectly classified as a collision between two ordinary black holes with strange parameters. We may have already detected these exotic mergers without even realizing it, their true nature hidden in plain sight within our data. This revelation forces a complete re-evaluation of the entire population of gravitational wave events catalogued so far. Take, for example, the famous first detection, GW150914. That signal was interpreted as the merger of two black holes around 30 times the mass of our Sun. But what if one of those objects wasn't a black hole at all? The resulting waveform would be altered. The estimated masses, spins, and even the distance to the event could be systematically wrong if we've been using the wrong model to decode the message. It necessitates a painstaking reanalysis of past data, creating new banks of waveforms that include these exotic possibilities. It's like realizing you've been translating an ancient language using the wrong dictionary. You have to go back to the original text and start over with the correct grammar. For future observations, the implications are even more profound. The discovery gives astronomers a specific new signature to search for. Teams at LIGO, Virgo, and the soon-to-be operational Kagra Observatory in Japan can now write new algorithms to scan incoming data for the unique gravitational wave fingerprint of a merger involving a mass gap object. They can look for telltale signs in the signal, like a specific resonance or an unexpected deviation in the ring-down phase that might point to the exotic nature of one of the merging bodies. It transforms this object from a solitary anomaly into a template for an entire new class of cosmic event. We're no longer just listening for collisions, we're hunting for the weird ones, the outliers that could reveal entirely new physics. Furthermore, the extreme spin of this object adds another layer of complexity. Spin has a dramatic effect on a binary system's dynamics. Two rapidly spinning black holes that are aligned with their orbital axis will spiral indifferently than two that are misaligned or spinning slowly. An object with a spin teetering on the theoretical maximum would impart a unique imprint on the gravitational wave signal as it whirls around its partner. This could produce a detectable precession, a wobbling in the orbital plane that would be a clear marker of something extraordinary. Finding that signature in a future LIGO signal would be the ultimate confirmation, directly linking this one puzzling object to the grand cosmic dance of mergers happening all across the universe. Ultimately, this discovery pushes gravitational wave science from an era of confirmation into an era of exploration. The first few runs were about proving Einstein right and opening the window. Now, with this new mystery, the data becomes a tool for probing the very edges of known physics. Each new chirp from the cosmos isn't just a story about a collision. It's a potential test for whether such exotic objects are common or rare, and a direct probe of their behavior in the most extreme gravitational environment possible. The silent spin of this one celestial rebel is now dictating the future of how we listen to the universe, ensuring that with every new ripple we detect, we'll be asking a more profound question. Are we hearing a familiar tune, or is the universe composing an entirely new kind of music? But the cosmic detective story doesn't end with gravity and quantum foam. There's another titanic force at play in the universe, one that can twist the fabric of reality in its own way: magnetism. Forged in the turbulent hearts of stars and amplified in cosmic dynamos, magnetic fields are the invisible sculptors of the cosmos, and they might just hold a key piece of this puzzle. Could an extraordinarily powerful magnetic field be the secret behind this object's impossible spin, warping our observations to create an illusion that defies the laws of physics? To understand how, we need to venture into the complex world of magnetohydrodynamics, or MDH, the science of how magnetic fields and electrically conducting fluids like the plasma in an accretion disk interact. Imagine that seething whirlpool of superheated gas not as a simple fluid, but as a roiling sea of charged particles. In the presence of a magnetic field, these particles become trapped, forced to spiral along the field lines like beads on an invisible wire. This fundamentally changes how the accretion disk behaves. Instead of smoothly spiraling inward, the gas gets channeled, accelerated, and even launched away in powerful jets, all orchestrated by the magnetic field's immense power. Now consider the impact of a truly monstrous magnetic field anchored to this spinning core. If this object is a neutron star descendant, a magnetar with a field 1,000 trillion times stronger than Earth's, that magnetic force would dominate everything for light years around. It would act like a colossal brake, exerting a powerful torque on the inner edge of the accretion disk. This magnetic braking effect could drastically alter the dynamics, slowing down the flow of material in some regions and accelerating it in others, creating violent turbulence and shock waves within the plasma. Our primary method for measuring spin relies on interpreting the light from that inner disk. If a magnetic field of that magnitude is churning the plasma into a frenzy, it could massively distort the ion emission line, smearing it out in a way that perfectly mimics the signature of a black hole spinning at the absolute limit. We might not be looking at a violation of physics at all, but rather a monumental magnetic masquerade. This magnetic influence could extend even further, potentially propping up the entire structure of the object itself. The outward pressure from an incredibly dense, wound-up magnetic field could provide crucial support against the relentless crush of gravity, helping an object that should have collapsed into a black hole remain stable. This would neatly explain its presence in the mass gap. It would be a magnetar, but on steroids, an object so massive and so magnetized that it has entered a new regime of stability we've never witnessed before. The faint periodic emissions we detect could then be explained as starquakes on its solid, magnetized crust or pulses from its magnetic poles, a behavior well documented in neutron stars but thought to be impossible for a black hole. However, there's a significant challenge to this magnetic hypothesis. Maintaining a magnetic field that powerful requires a dynamo effect, a self-sustaining engine usually fueled by the rapid convection of conducting material in a spinning core. For a standard neutron star, this dynamo action is thought to fade over time as the star cools and its rotation slows. An object this old, having siphoned mass from a companion for millions of years, should have seen its magnetic field decay considerably. The fact that it apparently hasn't suggests its internal engine is unlike anything we know. Perhaps its sustained high spin rate, fueled by its binary companion, keeps its internal dynamo perpetually churning. Or maybe its core is composed of a new, exotic type of superconducting matter that can sustain a permanent, frozen-in magnetic field of unbelievable strength. The very possibility pushes the boundaries of what we believe is magnetically possible in the universe, offering a thrilling, if incredibly complex, solution to the mystery of the spinning black star. This very idea of a lawless singularity exposed to the universe was so troubling to the physics community that it prompted one of the most influential conjectures in modern cosmology. Back in 1969, the renowned physicist Roger Penrose proposed what he called the cosmic censorship hypothesis. Think of it as nature's ultimate firewall against chaos. Penrose's conjecture was elegant in its simplicity. Nature abhors a naked singularity. It posits that whenever a singularity forms from gravitational collapse, the laws of physics will always ensure it is hidden from the rest of the universe behind a protective curtain, the event horizon of a black hole. This isn't just a suggestion, it's a foundational principle that has undergirded decades of black hole research. It ensures the universe remains predictable and that the well-defined laws of causality we rely on don't break down at its most extreme edges. A naked singularity would be a point where gravity becomes infinite and our equations spit out nonsense, a place where prediction becomes impossible and the past no longer determines the future. Cosmic censorship is the hypothesis that physics itself steps in to prevent such a reality-bending paradox from ever being observable. Our spinning black star now stands as perhaps the most serious potential violation of this cosmic rule ever observed. Its inferred spin rate, pushing past the Kerr limit, directly implies the dissolution of its event horizon. If that is true, we are not just looking at a new type of object. We are potentially staring directly into the heart of a naked singularity, the very thing Penrose argued the universe conspires to censor. It would be the ultimate cosmic taboo laid bare for us to see. The implications of this are staggering, far beyond a simple classification problem for astronomers. A verified naked singularity would be more than just an oddity. It would represent a fundamental breakdown in our ability to describe nature, the deterministic fabric of the universe where cause reliably precedes effect, could begin to fray at the edges of this gravitational anomaly. The very notion of predictability, which is the bedrock of the scientific method, would be challenged. This is why the scientific community is treating this discovery with such a potent mix of excitement and profound caution. The possibility that we might be witnessing the unthinkable, a crack in nature's censorship, forces us to confront the limits of our knowledge in the most dramatic way possible. It pushes us to ask not just what this object is, but whether the universe's deepest laws might be more flexible or more strange than we ever dreamed. Resolving this mystery will require more than just better observations. It might demand a new physics, one that can finally reconcile the warring worlds of the infinitely large and the infinitely small. Pinpointing the exact nature of this object is like trying to read the fine print on a sign from 15,000 miles away through a thick, turbulent atmosphere. The very qualities that make it so fascinating also make it incredibly difficult to study. Our primary challenge is its darkness. It doesn't emit its own light, so we're entirely reliant on interpreting the behavior of the matter and space around it. The companion star is our main source of information, but its light gets distorted not just by the object's gravity, but by the interstellar medium, the vast clouds of gas and dust that lie between us and it. This dust can scatter and redden the starlight, subtly altering the measurements we depend on to understand the system's dynamics. It's like trying to listen to a faint, beautiful melody while someone is vacuuming in the next room. The signal is there, but it's buried under a layer of distracting noise. Furthermore, the accretion disk itself is a source of complication, not just clarity. Our models assume a certain level of stability in this swirling vortex of plasma, but in reality, it's likely a chaotic mess. Magnetic instabilities can cause flares and outbursts that temporarily swamp the delicate ion emission line we're trying to measure. The disk might also be warped or tilted, meaning we're not getting a clean, face-on view of the system, which would skew our interpretations of its spin. Every observation is a snapshot of an incredibly dynamic and violent environment, and we have to be cautious not to mistake a temporary tantrum of the disk for a fundamental property of the central object. We are, in essence, trying to deduce the precise speed and shape of a spinning top by only studying the ripples it makes in a choppy, stormy pond. This is why the astronomical community is not resting on a single set of observations. The key to cracking this case lies in long-term, multi-wavelength monitoring. By watching this system over years, even decades, we can average out the short-term fluctuations and see the underlying stable behavior. Radio telescopes like the Very Large Array are listening for any faint whispers of radio waves that might be associated with jet activity or pulsar-like emissions. Infrared observatories like the James Webb Space Telescope are peering through the cosmic dust, trying to get a clearer picture of the companion star and the structure of the accretion disk itself. Each different wavelength of light gives us a separate piece of the puzzle. What confuses us in X-ray might become clear in infrared and vice versa. The future of this investigation, however, shines brightest with the next generation of observatories currently in development. The European Space Agency's Athena mission, slated for launch in the 2030-50s, is a dedicated X-ray observatory designed to be hundreds of times more sensitive than current instruments. Athena could study the ion emission line from this object with unprecedented precision, potentially mapping the distortions in space-time around it in enough detail to finally confirm or rule out the presence of an event horizon. It could watch the system in real time as clumps of matter spiral in, giving us a direct movie of how space is being dragged around the central engine. Even more revolutionary is the prospect of space-based gravitational wave observatories. The Laser Interferometer Space Antenna, or LISA, is a mission planned to consist of 3 spacecraft flying in a giant triangle millions of miles across, trailing behind Earth in its orbit around the Sun. Free from the seismic noise of our planet, LISA will be able to detect the low-frequency gravitational waves produced by massive objects spiraling together over time. If our mysterious object is in a binary system with its companion, it should produce a steady, faint hum of gravitational waves. By listening to this hum, LISA could measure the system's parameters, its mass and spin with astounding accuracy, completely independent of the messy complications of light and accretion disks. It would provide a direct, clean readout from the gravity itself, potentially delivering the definitive answer we've been searching for. And on the far horizon, the ultimate tool for solving such mysteries is taking shape. The Event Horizon Telescope network is expanding. By adding new radio dishes across the globe and even planning for future space-based components, the EHT aims to achieve resolution so sharp it could potentially resolve the immediate environment around this object. While it might not see a detailed shadow like it did for M87, it could discern whether there's a clear event horizon or a more complex solid surface. Each new telescope, each new mission, brings a new sense of focus to the blurry image we have today, slowly turning a puzzling shadow into a detailed portrait that will, we hope, reveal the true face of this cosmic rebel. This discovery has sent a shockwave through the theoretical physics community, forcing every major school of thought to confront an observation that challenges their most foundational principles. Each framework, from the tiny vibrating strings of string theory to the woven loops of space-time in loop quantum gravity, is being pushed to its limits, attempting to craft an explanation for an object that simply should not be. String theory, which posits that the fundamental constituents of reality are unimaginably small, vibrating strings, offers a fascinating possibility. In this framework, the concept of a point-like singularity, a core of infinite density, might be an illusion, a mathematical artifact of an incomplete theory. String theory suggests that at the tiniest scales, close to what's known as the Planck length, the traditional smooth geometry of space-time predicted by general relativity gives way to a frothy, discrete structure. This could prevent matter from collapsing into a true singularity. Instead, this object could be what string theorists call a fuzzball, a star-sized knot of tangled strings whose surface looks and acts very much like an event horizon from afar, but is actually a defined, though exotic, structure. This fuzzball could potentially spin at extreme rates without violating physical laws, as the strings themselves provide a quantum mechanical structure that stops the collapse and might even allow for the faint emissions we detect, resolving the information paradox in the process. On a different path, loop quantum gravity takes an even more radical approach to the problem of the singularity. This theory proposes that space-time itself is not smooth and continuous, but is woven from a network of finite, discrete loops. This granularity of space introduces a fundamental limit to how tightly matter can be compressed. It simply cannot be crushed into an infinitely dense point. In the loop quantum gravity model, the immense gravitational collapse of a dying star would eventually be met with a powerful repulsive force generated by the quantum geometry of space itself, causing a bounce rather than a collapse. What we perceive as a black hole could actually be a transition to a white hole, a region where matter and energy are expelled. For this spinning black star, its impossible stability and lack of a classical event horizon could be explained if it is not a black hole at all, but a black hole remnant in a slow, stabilized bounce phase, constantly recycling energy and information in a way that appears as a stable, massive, spinning object from the outside. Meanwhile, some physicists are looking beyond modifications to gravity and are investigating the properties of matter itself under such extreme conditions. They are revisiting the equation of state for neutron star matter, asking if there is an unknown, ultra-stiff phase of matter that could support a core against collapse at masses previously thought impossible. Perhaps under pressures so great that atomic nuclei dissolve into a soup of quarks and gluons, a new state of matter emerges, a quark star or a color superconductor, that is significantly more resistant to gravitational collapse than our current models allow. This object could then be the first observed example of a stable quark star, its incredible density and rigidity allowing it to sustain a rapid rotation that would tear a standard neutron star apart. Its faint pulses could be vibrations in this super-dense exotic matter, and its gravitational pull would be nearly indistinguishable from a black hole of the same mass, neatly placing it in the mysterious gap and challenging our definitions. The very existence of this object forces a profound philosophical shift in how we approach cosmic mysteries. It demonstrates that we cannot solely rely on pure theory or pure observation. We need a constant dynamic dialogue between the two. A discovery like this is the ultimate experiment, one set up by nature itself on a galactic scale, and it provides a critical benchmark against which we can test the predictions of these competing and often mathematically abstract theories. The theories that can successfully incorporate this anomaly into their framework, predicting its behavior and suggesting new, observable signatures, will gain tremendous credibility. Those that cannot may need to be refined or even set aside. This is the scientific process at its most powerful and exciting, an unexpected result that doesn't just add a new data point, but has the potential to steer the entire direction of fundamental physics for decades to come, guiding us closer to that elusive theory of everything. This pattern of disruptive discovery is woven throughout the history of science, where a single, stubborn anomaly has repeatedly shattered our comfortable understanding and forced a revolutionary new view of reality. Consider the humble orbit of Mercury in the late 19th century. For generations, astronomers had meticulously charted its path, and they found a tiny, persistent glitch. The point in its orbit closest to the Sun, its perihelion, was slowly drifting, precessing at a rate that could not be accounted for by Newton's laws of gravity and the known gravitational tug of the other planets. This was a minuscule discrepancy, just 43 arcseconds of drift per century, but it was real and it was unexplained. For decades, it was a nagging puzzle, a quiet whisper that something was incomplete in Isaac Newton's seemingly perfect cosmic clockwork. The solution did not come from a minor adjustment to the existing model. It required a complete overhaul of our conception of gravity itself. Albert Einstein's theory of general relativity, which reimagined gravity as the warping of space-time by mass, perfectly predicted that exact tiny drift. What was once an embarrassing anomaly became the first glorious proof of a new physics. We see this pattern again in the early 20th century with the ultraviolet catastrophe, a name that perfectly captures the scientific turmoil it caused. Physicists had a beautifully elegant model for how a hot object, like a blacksmith's iron or a star, should radiate energy. The equations predicted that as the wavelength of light got shorter, moving into the ultraviolet range, the energy output should skyrocket towards infinity. This was not only nonsensical, it was completely at odds with what experiments actually showed. The real world demonstrated that energy radiation peaked at a certain wavelength and then fell off. This wasn't a small error, it was a total failure of classical physics at the atomic scale. Max Planck, desperate to find a mathematical solution, made a radical proposal. Perhaps energy is not emitted in a smooth, continuous wave, but in tiny, discrete packets he called quanta. This idea was so heretical that even Planck saw it as a mere mathematical trick, but it worked. It perfectly described the experimental data. This anomaly, this catastrophic failure of the old models, directly planted the seed for quantum mechanics, a theory that now underpins all of modern technology and our understanding of the subatomic world. The discovery of dark matter follows this same arc of an observation refusing to conform to theory. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. According to Newton and Kepler, stars on the outer edges of a galaxy, far from the central mass of stars, should orbit much more slowly than those near the center. But Rubin's meticulous observations of galaxy after galaxy revealed something astonishing and unequivocally wrong. The stars on the outskirts were moving just as fast as those near the core. It was as if each galaxy was embedded in a massive, invisible sphere of matter providing extra gravitational pull. The data did not match the prediction, and rather than dismissing the data, scientists were forced to invent a whole new form of matter that does not interact with light, dark matter, to explain it. This one observational anomaly revealed that the universe we see is only a tiny fraction of what actually exists. Our spinning black star is the latest chapter in this grand tradition. It is not an error to be explained away, it is an invitation. It is our generation's Mercury perihelion, our ultraviolet catastrophe. Its impossible spin and its residence in the mass gap are the data points that don't fit, the whispers that our maps of reality are still missing entire continents of understanding. Just as those past anomalies were the gateways to relativity and quantum mechanics, this object could be our gateway to the next great synthesis, a theory that finally reconciles the immense gravity of Einstein's cosmos with the bizarre probability of the quantum world. History shows us that it is precisely these moments of beautiful confusion, these cosmic rebels that break the rules, that propel human knowledge forward in its greatest leaps. Perhaps the most mind-expanding possibility of all is that this spinning black star isn't just a puzzle within our universe, but a window into another one entirely. The multiverse hypothesis, once confined to the speculative edges of cosmology, suggests our universe might be just one bubble in a vast cosmic foam of universes, each with its own unique set of physical laws and constants. What if this object isn't a break in our universe's rules, but an imprint of rules from a different cosmos altogether? Think of it like a strange seashell washing up on a beach. Its unique shape and structure don't belong to that local environment, hinting at a distant, different ocean from which it came. This black star, with its defiance of our local physics, could be the cosmic equivalent of that seashell, a piece of exotic driftwood from a foreign universe with different fundamental parameters. In such a multiverse scenario, the formation of this object might be explained by a rare and cataclysmic event, a collision or a close gravitational encounter between our universe and a neighboring bubble in the multiverse foam. During this brief, violent interaction, the fundamental forces in that localized region of space might have been temporarily altered. The constants that govern the strength of gravity or the behavior of matter under extreme density could have shifted, allowing a star to collapse in a way that is normally forbidden by our universe's laws. The resulting object, this spinning black star, would then be a fossilized remnant of that event, a stable structure built under a different set of blueprints that somehow persisted even after our local physics reasserted itself. Its impossible spin and mass would be perfectly normal for its place of origin, making it an anomaly only from our limited, single-universe perspective. Testing such a fantastical idea might seem impossible, but physicists have proposed methods to hunt for these cosmic fingerprints. If the object's core is indeed governed by physics from another universe, it might exhibit a fundamental symmetry breaking that is different from our own. This could manifest in the way it interacts with certain particles. We could search for an anomalous signature in the high-energy cosmic rays that might emanate from its vicinity, looking for particles or energy patterns that don't align with the standard model of particle physics. Furthermore, if the multiverse collision altered the very fabric of space-time in that region, it might have created a subtle gravitational lensing effect that is unique and detectable with future ultra-sensitive telescopes. The Event Horizon Telescope, as it expands its network, could potentially look for microscopic wrinkles or distortions in the space around the object that can't be explained by general relativity alone. The most compelling test, however, might involve a search for siblings. If one such object was created by a multiverse event, the probability is that it wouldn't be alone. Astronomers would need to scour the sky, particularly in the same general region of the galaxy, searching for other anomalous compact objects with similar impossible properties. Finding a cluster of these rule breakers would be powerful, albeit circumstantial, evidence that a local event altered physics in that part of space, rather than us having to rewrite the laws for the entire cosmos. It would suggest a puncture in the fabric of our universe, a place where the walls between realities are thin, and where the laws of nature are not quite as immutable as we once believed. While firmly in the realm of speculation for now, this line of inquiry demonstrates how a single unexplained discovery can push us to consider the most profound questions about the nature of reality itself. While the idea of harnessing a naked singularity might sound like the plot of a science fiction epic, this discovery forces us to confront the practical, long-term implications for our future as a spacefaring civilization. The immediate reaction might be to see this object as a terrifying cosmic hazard, a region of broken physics that any sane pilot would avoid by light years. And that caution is warranted. The gravitational forces and potential for unpredictable space-time distortions around such an anomaly would be unlike any navigational challenge we've ever conceived. However, the history of human progress is written by those who look at a dangerous, unknown force and ask not just how to avoid it, but whether it can ever be understood and perhaps even utilized. The most tantalizing, though distant, possibility lies in the realm of propulsion. Our current methods of traversing the immense gulfs between stars are shackled by the tyranny of rocket fuel and the absolute speed limit of light. Concepts like Alcubierre drives, theoretical engines that compress space-time in front of a ship and expand it behind, offer a dream of faster-than-light travel but require forms of energy density that border on magic with our current knowledge. A stable, high-spin object like this could, in principle, create a natural and profound distortion of space-time. If its properties could be mapped and understood, it might serve as a natural laboratory for studying these effects up close. The knowledge gained wouldn't be about building an engine around a black hole, but about reverse engineering the physics that allow it to so dramatically warp the universe, potentially informing new technologies that could create miniature, controlled distortions for propulsion. Beyond travel, the energy implications are staggering. We already know that a spinning black hole's ergosphere is a region of immense rotational energy that could, in theory, be extracted through clever processes. An object spinning at or beyond the classical limit would have an ergosphere of unprecedented ferocity. The ability to tap into that energy, even from a safe distance, would represent a power source of astronomical scale, far beyond anything fission, fusion, or antimatter could ever provide. It could power entire civilizations or serve as a gravitational slingshot on a galactic scale, accelerating spacecraft to relativistic velocities without a single drop of fuel. This isn't about plugging a cable into a black hole. It's about understanding the fundamental dynamics so well that we could, for instance, use carefully aimed particle beams to steal a fraction of that spin energy as it is released back into the universe. Perhaps the most profound practical application is the most abstract computation. The extreme conditions around such an object, where quantum mechanics and gravity are forced to interact, might create a natural environment for processing information in ways our flat, calm space-time cannot support. Theoretically, the incredible density of events and interactions could be harnessed for forms of computation that are literally impossible for any silicon-based computer operating under normal physics. While this remains firmly in the realm of speculation, it underscores a critical point. Mastering the physics of this phenomenon isn't just about answering a cosmic riddle. It's about expanding the entire toolkit of what is physically possible for advanced civilization. The technologies that would emerge from such a deep understanding wouldn't necessarily look like a black hole generator. They might look like entirely new branches of engineering based on principles we are only just beginning to glimpse. This mysterious spinning object, therefore, isn't just a curiosity for astronomers, it's a glimpse into a possible future chapter of physics itself, one that could unlock capabilities for humanity that we currently relegate to the pages of fantasy. When news of this cosmic rebel first broke beyond the pages of academic journals, it ignited a firestorm of public fascination that was as immense as it was instantaneous. Headlines around the world scrambled to capture the sheer weirdness of the story, often landing on a familiar but potent phrase, the black hole that shouldn't exist. This framing was a masterstroke in science communication, instantly conveying both the object's profound mystery and its direct challenge to established authority. It wasn't just a new discovery, it was a cosmic rule breaker, an underdog narrative that resonated deeply. Social media platforms lit up with a mix of awe, memes, and genuine curiosity. For a few days, the intricacies of the Kerr metric and the mass gap became unlikely topics of discussion in comment sections and around dinner tables, a testament to the public's enduring appetite for cosmic wonder and the mysteries that lie at the very edge of human understanding. This wave of interest, however, also highlighted the perennial challenge of translating complex astrophysics into digestible soundbites without losing crucial nuance. Many mainstream news outlets did an admirable job focusing on the core mystery, an object in the forbidden zone spinning too fast, and interviewing the cautious, excited scientists behind the discovery. They accurately presented it not as a definitive overturning of physics, but as a tantalizing puzzle that was pushing the boundaries of knowledge. Reputable sources used careful language, explaining that this was a potential challenge to models, not an outright disproof of Einstein. They served as a vital bridge, allowing the public to peer into the rigorous, often painstaking, process of scientific discovery, where a single anomaly can take years to confirm and even longer to understand. Yet, as with any story that brushes against the profound and unknown, sensationalism was an ever-present temptation. A subset of media coverage, particularly on more fringe platforms and in click-driven online ecosystems, veered into more dramatic territory. Here, the careful could and might of the scientific press releases were often replaced with definitive does and is. Some segments framed the discovery as proof that Einstein was wrong, a gross oversimplification that ignores how science actually progresses. Even more extreme outlets leaped to wilder conclusions, tenuously linking the object to ancient aliens, prophecies, or harbingers of doom, completely untethering the discovery from its factual moorings and exploiting the public's fascination for clicks. This media ecosystem creates a fascinating feedback loop with the scientific process itself. The immense public interest generated by both accurate and sensationalized reports translates into something incredibly valuable: support. Buzzworthy discoveries capture the imagination of policymakers and funding agency committees, helping to secure the financial backing for the next generation of telescopes and space missions needed to solve the mystery. The public's thirst for answers, stoked by media coverage, directly fuels the scientific momentum to find them. However, this spotlight also places a burden on the researchers involved, who must suddenly navigate a blizzard of interview requests while carefully managing expectations, constantly reiterating that science is a marathon of verification, not a sprint to spectacular headlines. Ultimately, the public's embrace of this spinning enigma, filtered through the lens of media, reflects something timeless. It is a modern echo of humanity's ancient urge to gather around a campfire and share stories about the strange and wonderful lights in the sky. We are a species hardwired for curiosity, and the universe has presented us with a brilliant new campfire tale. The media, in its myriad forms, is simply the megaphone for that story, amplifying both our collective wonder and our shared desire to understand our place in a cosmos that remains gloriously and stubbornly mysterious. This confrontation with the impossible forces us to pause and ask a deeper, more philosophical question that often goes unspoken in the rush of discovery. Just because we can pursue a certain piece of knowledge, does that always mean we should? The quest to understand this spinning black star isn't just a technical challenge, it's an ethical one, forcing us to consider the responsibilities that come with probing the most fundamental layers of reality. Throughout history, the pursuit of pure knowledge has been humanity's greatest driving force, leading to revolutions in thought and technology that have reshaped our world. Yet, there is a long and sobering tradition of scientific discovery arriving with unintended consequences, from the power of the atom to the potential of genetic engineering. The act of tearing back the veil on a cosmic secret, especially one that might involve a naked singularity, carries a weight that extends far beyond the astronomy community. At the heart of this ethical dilemma is a concept known to philosophers as the Pandora's box problem. Some knowledge once gained cannot be unknown. If our investigation into this object were to somehow confirm the existence of a stable, observable naked singularity, it would fundamentally shatter our current understanding of causality, the principle that cause must always precede effect. This isn't just an abstract concern for physicists, it strikes at the very core of a predictable, rational universe. A realm where the laws of physics break down could, in theory, become a realm where prediction becomes impossible, where the logical chain of events we rely on for everything from engineering to jurisprudence no longer holds firm. The pursuit of this knowledge pushes against a boundary that some argue should remain theoretical, a warning sign placed by nature itself to prevent us from venturing into a domain we are not equipped to handle. This leads to a contentious debate within the scientific community itself. On one side are the purists who argue that the pursuit of knowledge for its own sake is the highest calling of our species, and that to shy away from a mystery due to potential philosophical discomfort is a form of intellectual cowardice. They point out that every major leap in human understanding, from Copernicus placing the sun at the center of the solar system to Darwin outlining evolution, was initially met with profound existential anxiety. That discomfort, they argue, is not a reason to stop but a sign that we are on the verge of a transformative breakthrough. The potential benefits of mastering such physics, perhaps unlocking new forms of energy, understanding the true nature of space-time, or even securing the long-term future of our civilization, are so monumental that they outweigh the abstract risks. Opposing this view are the cautionaries who advocate for a principle of epistemological humility. They suggest that some domains of nature might be inherently beyond human comprehension, not because we aren't smart enough, but because the act of observing or interacting with them could be inherently destabilizing. They draw a parallel to the famous thought experiment of Schrödinger's cat, where the act of observation itself determines the outcome. If a naked singularity exists, our very attempts to measure it could have unpredictable effects, not just on the object, but on the causal structure of space-time in its vicinity. This isn't about fear of the unknown, but a respect for the possibility that the universe has built-in safeguards, and that prying them open could have ramifications we are utterly unequipped to foresee. Navigating this divide requires a new framework for scientific ethics in the age of fundamental discovery. It calls for a proactive approach where cosmologists, ethicists, and philosophers collaborate long before a definitive answer is found. We need to establish guidelines for how to responsibly explore such frontiers, much like the international protocols that govern certain types of biological research. This might involve developing containment theories, mathematical models that predict the potential reach of a destabilized physical law, or creating simulation-based red lines that tell us when an experimental pursuit is veering into potentially dangerous territory. The goal wouldn't be to stifle inquiry, but to ensure that our insatiable curiosity is matched by a profound sense of responsibility, guaranteeing that humanity's next great leap into the cosmos is taken with eyes wide open to both the wonder and the weight of what we might find. This discovery is already sending ripples through lecture halls and seminar rooms, forcing educators to confront a delightful but challenging problem. How do you teach established physics when a cornerstone example might be breaking the rules? For decades, introductory astrophysics courses have presented a clean, almost tidy picture of stellar graveyards. The life cycle of a star culminated in one of two neat endpoints, a neutron star or a black hole with a clear mass boundary between them. This binary classification was a staple of textbooks and exam questions, a fundamental concept students were expected to memorize and understand. Now, with the appearance of this spinning enigma squarely in the mass gap, that simple dichotomy has collapsed. Professors can no longer present this area of astrophysics as a settled matter. Instead, they must introduce it as a living, breathing mystery, showcasing the very process of scientific discovery as it unfolds in real time. The curriculum in advanced general relativity courses is undergoing an even more profound shift. Where once the care solution for a rotating black hole was presented as the final word, a beautiful and complete mathematical description, it is now being taught with a crucial asterisk. Lectures now include dedicated modules on the limits of the Kerr metric, discussing the cosmic censorship hypothesis not as an abstract philosophical idea, but as a testable principle that current observations are actively challenging. Students are being given the actual data from this system as a case study, tasked with running the models themselves to see how the equations break down. This transforms their learning from passive reception of knowledge to active participation in a frontier debate, giving them a taste of the thrilling and often frustrating work at the cutting edge of theoretical physics. Textbook publishers are facing a unique dilemma. Do they rush to include a new section on mass gap objects and exotic compact remnants, knowing that the definitive explanation for this phenomenon could still be years or even decades away? The most forward-thinking are opting for a new approach, digital, living textbooks that can be updated with new discoveries and supplemented with direct links to the latest preprint research papers. The static, authoritative tone of traditional textbooks is giving way to a more dynamic and honest narrative that acknowledges the limits of our current understanding and celebrates the questions yet to be answered. This teaches an invaluable lesson to the next generation of scientists. That uncertainty is not a failure of knowledge, but the engine of its growth. This object is also becoming a central character in courses on the philosophy of science. It serves as a perfect modern example of a Kuhnian paradigm shift in its earliest stages, where an anomaly has appeared that the prevailing paradigm cannot explain. Students debate whether this will require a simple amendment to existing theories or a wholesale revolution that overthrows our current understanding of gravity. They explore the ethical responsibilities of scientists communicating such a complex and easily sensationalized discovery to the public. This enigma, therefore, is doing more than just updating facts. It's shaping how we think about the scientific method itself, reinforcing that science is not a collection of answers but a structured, never-ending process of asking better and better questions. Solving a mystery of this cosmic magnitude requires a global brain trust, a united front of the world's finest minds and most advanced technology. No single nation, no solitary telescope could ever hope to unravel the secrets of this spinning enigma alone. This is an endeavor that spans continents and cultures, a testament to how modern astrophysics operates as a truly international enterprise, where rivalries are set aside in the shared pursuit of understanding. From the high deserts of Chile to the frozen plains of the South Pole, from orbiting satellites to vast radio arrays, the world has turned its collective gaze toward this one patch of sky, pooling resources, data, and intellect in a coordinated effort that is as breathtaking as the discovery itself. The heart of this collaboration beats within a network of time allocation committees and data sharing agreements. When the first puzzling data trickled in from the Pan-STARRS survey in Hawaii, an automatic alert was sent out across the astronomer's telegram, a rapid-fire notification system that instantly informs observatories worldwide of something strange requiring immediate follow-up. This triggered a carefully orchestrated chain of events. The team that made the initial discovery didn't hoard their precious observing time. They immediately began collaborating with other groups, making the case for why this object deserved precious hours on other, more specialized instruments. A consortium was quickly formed, bringing together experts in X-ray astronomy, optical spectroscopy, and gravitational wave physics from institutions in the United States, Europe, Japan, and Australia. This global task force then began a meticulous campaign of multi-wavelength observation, a celestial relay race dictated by the rotation of the Earth. As the object set for telescopes in Hawaii, it was rising for the powerful Very Large Telescope array high in the Atacama Desert of Chile. The European Space Agency's XMM-Newton satellite, orbiting high above the planet, could maintain an unbroken watch, its data downlinked to a processing center in Spain before being shared with analysts in California and India. The New Star telescope, with its unique ability to focus high-energy X-rays, dedicated its valuable time to staring intently at the system, its data adding another crucial piece to the spectral puzzle. This around-the-clock monitoring is essential to catch the object's faint and variable emissions, ensuring that a cloud passing over one telescope doesn't mean a critical data point is lost forever. Perhaps the most powerful symbol of this international spirit is the Event Horizon Telescope collaboration. Though initially focused on imaging the supermassive black holes in M87 and our own galactic center, the EHT is a perfect example of what global cooperation can achieve. It is not a single telescope, but a planet-scale virtual instrument created by synchronizing a network of radio dishes from the high mountains of Mexico and Arizona to the frigid landscapes of Greenland and the South Pole, and across to the peaks of Spain and Hawaii. Data from each site is recorded on banks of hardened hard drives, which are then physically flown to central processing centers in Germany and Massachusetts, where supercomputers combine them using atomic clock precision. While this particular object may not yet be a primary target, the techniques and global infrastructure developed by the EHT are directly applicable to studying it, demonstrating how investment in one area of fundamental science creates a toolkit that benefits all others. This level of cooperation extends beyond hardware into the very culture of science. The teams analyzing the data are incredibly diverse, with graduate students in Tokyo working alongside senior professors in Paris and software engineers in Chile. They communicate through daily video conferences held at all hours to accommodate different time zones, sharing preliminary findings on open-access online repositories long before formal publication. This rapid, transparent exchange is crucial for weeding out errors and building upon each other's insights in near real time. What emerges from this process is not just a set of data points, but a shared narrative, a collective story being written by hundreds of authors from dozens of countries, all contributing their unique expertise to decode the message from a rebel star 15,000 light-years away. In a world often divided, it's a powerful reminder that the hunger for knowledge and the wonder of the unknown are universal traits that can bring humanity together to achieve the extraordinary. This discovery doesn't mark an end point, but a spectacular new beginning for black hole astronomy. It's as if we've been studying animals by looking at their footprints, and suddenly one has turned around, looked us in the eye, and roared something we can't yet understand. This object is no longer just a target for observation. It has become a living laboratory, a cosmic question mark that will dictate the research agenda for a generation of astronomers and physicists. The old, comfortable classification system is shattered, and in its place is a thrilling, uncharted territory filled with possibilities we are only starting to imagine. The immediate future of research will be dominated by a global, targeted campaign to find more of these cosmic rebels. For decades, surveys have been designed to find typical black holes and neutron stars. Now, we need to recalibrate our searches to specifically hunt for outliers lurking in the mass gap. This means writing new algorithms to sift through the mountains of data from observatories like the Vera C. Rubin Observatory, training them to recognize the subtle, telltale wobbles of a companion star orbiting something truly weird rather than something expected. The goal is to move from a sample of one to a population. Are these objects incredibly rare, one in a galaxy anomalies, or have they been hiding in plain sight all along, their strange signatures previously dismissed as instrument error or noise? Finding even a handful more would be revolutionary, allowing us to understand if this is a fluke or a fundamental new class of celestial object. This hunting strategy extends beyond light into the realm of gravitational waves. The data analysis teams at LIGO, Virgo, and CAGRA are now on high alert, urgently generating new banks of theoretical waveforms. These templates will model what the collision of a standard black hole with a mass gap object would sound like, or the even more exotic merger of two of these enigmatic entities. They will then rescour the entire catalog of past detections, listening for any faint, unusual chirp that might have been previously misclassified or overlooked. The next observing run for these gravitational wave observatories will be fundamentally different. It will be a dedicated hunt for the strange and unexpected, with this object providing the first key to decoding a new language of cosmic collisions. But finding them is only half the battle. The real challenge lies in developing entirely new theoretical frameworks to explain them. This will require a historic collaboration between astrophysicists and quantum gravity theorists, two groups that have often worked in parallel but are now forced into a direct dialogue. The mathematics of string theory, loop quantum gravity, and other candidate theories for quantum gravity will be moved from the abstract realm of pure theory and thrust into the crucible of observational testing. Can a particular string theory model accurately predict the precise spin limit this object seems to defy? Can a loop quantum gravity simulation replicate the stability we observe? For the first time, we have a concrete, observational benchmark against which to test these highly abstract ideas, potentially elevating one from a beautiful mathematical construct to a factual description of our universe. This effort will be powered by a new generation of computing. The supercomputers used for the current simulations are already among the most powerful on Earth, but they will need to be pushed to their absolute limits and beyond. We are entering the era of exascale computing and modeling the extreme environment around this object where warped space-time, turbulent plasma, and potential quantum effects all interact will be one of its primary tasks. These will be the most complex simulations ever attempted, requiring entirely new code that can blend the laws of general relativity with the rules of the quantum world. The digital universes created in these machines will be our primary testing ground, allowing us to safely break physics in silicon to see if we can make it match the impossible reality we see in the cosmos. Ultimately, the long-term goal is to move from speculation to confirmation, and that will fall to the next generation of telescopes now on the drawing boards. The European Space Agency's Athena X-ray Observatory, scheduled for launch in the 2030s, will be a game-changer. Its incredible sensitivity will allow it to study the ion emission line from this object with unprecedented precision, potentially mapping the warping of space-time around it in such detail that we could finally see the definitive signature of an event horizon or its shocking absence. Further out, the Laser Interferometer Space Antenna, or LISA, will open the low-frequency gravitational wave window, listening for the steady hum of this binary system. That hum would provide a direct, clean measure of its mass and spin, completely independent of the messy accretion disk physics, giving us a truth against which all our other models must be judged. The questions this object raises are even bigger than the answers it might provide. It forces us to ask if the mass gap is even real or merely an artifact of our previous ignorance. It challenges us to define what a black hole truly is. Is it defined solely by its event horizon, or can an object be black hole-like without one? Most profoundly, it asks whether the laws of physics are truly universal and immutable, or if in the most extreme corners of the cosmos, the rules can bend and new laws can emerge. This spinning enigma is more than a celestial body. It is a catalyst. It ensures that the future of astronomy will be anything but boring, guaranteeing that our journey to understand the darkest corners of the universe will be filled with wonder, confusion, and the thrilling promise of revolution. So where does this leave us with this cosmic rebel spinning silently in the darkness? It leaves us at the very edge of a new frontier, standing before a doorway we didn't even know existed a short time ago. This isn't just a story about one strange object. It's a powerful reminder that the universe is far more inventive and bizarre than our boldest theories. For centuries, we've been meticulously mapping the cosmos, building a rulebook for reality based on what we could see and measure. And just when we thought we had the final chapters on gravity and stellar evolution figured out, the universe sends us a brilliant, confounding exception to every rule. This spinning black star is that exception, a celestial exclamation point reminding us that discovery is not a destination, but a continuous, evolving journey. The implications of its existence ripple out across all of physics, touching everything from the fate of information to the very fabric of space and time. It challenges the clean, classical picture of black holes we've held for decades and forces us to seriously consider ideas that once belonged solely to the realm of theoretical fantasy gravastars, naked singularities, and universes where the constants of nature might not be so constant after all. This single anomaly has become a catalyst, pushing the entire field of astrophysics to ask better, more profound questions and to develop new tools to seek the answers. It proves that the most exciting words in science aren't "Eureka, I found it," but rather, "How, that's weird." This is how understanding truly evolves. It doesn't progress in a straight, predictable line. It lurches forward because of puzzles that refuse to be solved, because of data that stubbornly refuses to fit the model. Every great leap in our comprehension of the cosmos, from realizing the Earth revolves around the Sun to discovering the expanding universe, began with an observation that didn't make sense. Those anomalies are the engines of scientific revolution. They humble us, they frustrate us, and ultimately they expand our vision of what is possible. This spinning black star is our generation's great anomaly, a gift of profound confusion that is propelling us toward a deeper, richer understanding of the cosmos. And that is the most thrilling part of all of this. The mystery is still wide open. Right now, astronomers and physicists around the world are collaborating, debating, and poring over new data, trying to decode the true nature of this object. The story is still being written, and each of us gets to be a witness to this incredible moment of exploration. It's a powerful testament to human curiosity and our relentless drive to look out into the vast, dark unknown and demand to know what's out there. So the next time you look up at the night sky, remember that it is not a static picture. It is a living, dynamic, and deeply mysterious universe filled with phenomena that defy our current understanding. Let this spinning enigma be an invitation to stay curious, to embrace the questions we can't yet answer, and to always wonder what other impossible things are out there waiting to be discovered. The greatest cosmic mysteries are still ahead of us, hidden in the dark, just beyond the light of our knowledge, urging us to keep